Hey calculus friends, this is section 7.4 notes. Today we're going to be talking about differential equations, and we have seen these before this year. Differential equations are equations that represent the derivative of some function with respect to another. For example, the derivative of y with respect to x. We have seen and used differential equations already when we learned implicit differentiation and again when we worked on related rates problems. They're usually written in Leibniz notation, but can sometimes be written in the y prime notation as well. So now our goal is going to be to go backwards. If we have a differential equation that relates to quantities, what equation did that differential come from? In other words, finding a general or particular solution to a differential equation means we will have to integrate. Our steps for finding a general solution to a differential equation are going to be to, step one, separate our variables on the left side and the right side. Step two, integrate both sides, and I have a little note here, don't forget the plus c, we'll talk about that in a minute. And then step three, solve for the dependent variable, which is usually y, but it's the variable that is on the top of the differential. All right, so step one, we're going to separate our variables. So if we look at our given differential equation, we have dy dx equals 2x cubed. So the first thing I want to point out is that this differential depends only on our independent variable x. You can see that right here. We only have stuff on the right-hand side that has to do with x. So I'm just going to put a little note here. Note that the differential depends only on x, okay? So when we separate our variables, okay, think of the left side as a fraction, dy divided by dx. We want anything that has to do with x on the right-hand side, and we want anything that has to do with y on the left-hand side. So if I wanted to move that dx over to the other side, I would be multiplying both sides of the equal sign by dx. So I would end up with dy equals 2x cubed dx. Now, if there had been a y term or a y part of the term over on the right-hand side, then I would have to move that over to the left-hand side, and we will see some examples of that in the future. All right, so I've done my step one, which is the separate step. Step two is going to be the integrate step. So now I'm going to integrate both sides. Now, you don't see it, but remember, in front of that dy, there is a 1. So I'm going to write it just to remember that. 1 dy equals the integral of 2x cubed dx. All right, so now I'm going to integrate both sides with respect to the variable on that side. So on the left-hand side, the integral of 1 dy would just be y. And again, I'm going to write it right now. I'm going to write the plus c. Remember when we found our antiderivatives, we always have that plus c because we could have some unknown constant term, right? And on the right-hand side, when I integrate 2x cubed, well, first of all, I'm going to add 1 to my exponent, so that's going to become x to the 4th. And then if I divide 2 by 4, or multiply in front by the reciprocal of 4, which is 1/4, 2 times 1/4 becomes 1/2. So I end up with 1/2 x to the 4th plus c. Okay, so I want you to notice that we've got a plus c on the left and we've got a plus c on the right. Okay, first thing, those aren't going to cancel each other out. You can't say minus c and have them be gone. Because they could be two different c values. Okay, so it might make more sense for us to say this is c1 and this is c2. Okay, so then my step 3 is going to be to solve for my independent variable. So in this case, I am going to solve for y. Well, if I want to get y alone, then I end up with my 1/2 x to the 4th plus c2, and then I guess if I move that over to the other side, that would be c1. But I still end up with just some constant term here. Don't know what it is. It's a combination of the constant term from the left-hand side and the right-hand side. So normally, what mathematicians do when they do solving a differential equation is they don't worry about putting the plus c over here on this side. They only put the plus c on the right-hand side. So my final answer is going to be y equals 1/2 x to the 4th plus c. And again, just one constant term in our answer there, because you can combine all kinds of unknown constant terms together and you still have one unknown constant term. So we're just going to call it c. In example 2, now if we look at our new differential equation, note that we've got dy dt equals, so y is our dependent variable, t is our independent variable, and on the right-hand side of the equal sign, we have both y and t. On the right-hand side. Okay, so our first step, separate, is going to be a little bit more complicated this time. So step 1, I have dy dt is equal to, notice that on the right-hand side, I've got t squared times y plus 2t times y. I'm going to go ahead and I'm going to factor that y out because that'll make separating a lot easier. So then I've got y times t squared plus 2t. So now if I want to separate, basically I need to move the y to the left-hand side, which is going to be dividing by y. And I need to move the dt to the right-hand side, which is going to be multiplying by dt. Okay, so I've successfully separated my variables. Everything with y is on the left, everything with t is on the right. Step 2 is going to be to integrate both sides with respect to the variable that is on that side. Now on the left side, dy over y, I'm going to write that slightly differently. I'm going to write that as 1 over y dy, we'll talk about that in a second, is equal to, and then over here I have my t squared plus 2t dt, which is just a polynomial. Whoops, sorry, forgot my integral symbol there. All right, and again, remember, when we integrate the left side, we're not going to worry about the plus c. We're only going to put the plus c on the right side because all constant terms added together are still some unknown constant term, right? Okay, what is 1 over y the derivative of? That should be a recognizable derivative, and that is 1 over y is the derivative of natural log. So the integral of 1 over y is going to be ln of the absolute value of y. And then on the right-hand side here, we just have polynomial terms, right? So we're just going to think about the power rule in reverse there. So my first term is going to be t cubed, and I need to multiply by the reciprocal, so 1/3 t cubed. And then my second term is going to become t squared. And if I multiply by 1/2, 2 times 1/2 just makes that a 1 t squared. And then over here is where I need my plus c. All right, step 2, successfully done. I have integrated both sides with respect to the variable on that side. Now step 3, I have to solve for y. Okay, my y is stuck inside of a natural log right now. So the only way to get that y out is going to be to raise both sides to the base of e, right? So when I rewrite this, it's going to look like e to the power of ln y equals e to the power of 1/3 t cubed plus t squared plus c, and that's all in the exponent over there. So now the left-hand side, the e and the natural log just cancel each other out. E to the ln or ln to the e, remember those just undo each other. So we end up with the absolute value of y is equal to e to the 1/3 t cubed plus t squared plus c. Now, if I want to get rid of that absolute value around my y, because I want just y equals, remember that absolute value means that whatever is inside could have been positive or negative. So if I'm going to drop those absolute value bars, then that means that on the other side of the equal sign, I'm going to need a plus or minus in front of my term. So my y could be equal to either positive or negative e to the 1/3 t cubed plus t squared plus c power. And maybe put a little note there for yourself that the absolute value creates the possibility of plus or minus on the right side. Now, if we had an initial condition and we were able to solve for our c value, we would know whether we should be choosing the positive or negative, and we will get to that in the second half of our notes today. Okay, we're going to find a general solution. This time we have dy d theta, so y is our dependent variable, theta is our independent variable. And on the right-hand side of the equal sign, we have 6y squared secant squared 3 theta. So we do have both variables kind of mixed together on our right-hand side. So again, step one is going to be to separate. Okay, so I'll just start by rewriting what I have. I have dy d theta is equal to 6y squared times secant squared of 3 theta. So when I separate, I'm going to bring that y squared over to the left-hand side. So I'm going to have dy over y squared equals, now I'm going to leave the 6 with the secant squared of 3 theta, and then I'm going to move the d theta over to the right-hand side. All right, so I've successfully separated. Now my next step is going to be to integrate both sides. So when I integrate the left side, I have 1 over y squared dy is equal to, I'm going to pull that 6 in front of my integral symbol because remember, a coefficient does not affect integration. So then I'm going to have secant squared of 3 theta d theta. All right, when I integrate the left-hand side, think of y squared as being y to the negative 2 power. So if I add 1 to my exponent, it's going to be y to the negative 1. And then if I multiply by the reciprocal of negative 1, that's 1 over negative 1, which is just negative 1, y to the negative 1. That's the left-hand side. On the right-hand side, secant squared is the derivative of tangent. Okay, so I'm going to have tangent of 3 theta. But again, because I didn't just have theta, I had 3 theta, I have to think about how I would undo that chain rule. Chain rule would say that when I take the derivative of tangent 3 theta, I get secant squared 3 theta times the derivative of 3 theta, which would be 3. So if I'm differentiating and I multiply by 3, then to undo that chain rule, if I am integrating, I'm going to have to divide by 3. Okay, so that 3 in the denominator comes from undoing the chain rule of that 3 theta. And then again, I have my plus c. All right, so now I can clean this up a little bit. I have negative 1 over y is equal to, the 6 over the 3 can reduce to 2. So 2 tangent 3 theta plus c. And then, of course, the last step would be to solve for y. So basically, if I multiply both sides by y, and then I divide both sides by 2 tangent 3 theta plus c, I end up with, for my step 3, y is equal to negative 1 divided by 2 tangent of 3 theta plus c. And that is going to be my final answer for number 3. If we want to find a particular solution to a differential equation, then we need to be given an initial condition of our function so that we can find our value for c. So our steps for finding a particular solution to a differential equation are very similar to what we did previously. We just have a few extra steps. Step 1 is still going to be to separate the variables on the left and right side. Step 2 is going to be to integrate both sides, and don't forget your plus c on the right. And then step 3 is where we're actually going to use the initial condition to find the value of c. Once we find c, step 4, we plug c back in, and then step 5, we solve for y. So really it's just the using a given ordered pair to solve for c and then plugging that value back in before you solve for y. That's really the only difference here. All right, so let's begin with our first example. We have dy dx equals x over y, and then they are telling us that y of 0 equals -3. That means that 0, -3 is our initial condition. When x is 0, y is -3. All right, so step 1 is going to be our separate step. We have dy dx equals x over y. All right, so we need to move the y to the left-hand side. Because y is in the denominator, that's going to mean multiplying both sides by y. So we will get y dy equals, and then we have to move the dx over, so we're going to multiply both sides by dx, and we get x dx. Okay, separation complete. The next step is going to be to integrate both sides with respect to the variable on that side. So the integral of y dy is going to be equal to the integral of x dx. Both of these are just power rule in reverse, easy to integrate. So y will become 1/2 y squared. Remember, we don't worry about the plus c on the left. We only put the plus c on the right. So this is equal to 1/2 x squared plus c. All right, step 3, now we're going to use our initial condition, right? And our initial condition was when x is 0, y is -3. So when I plug those values in for x and y, this will allow me to find the value of c. So I get 1/2 times -3 squared is equal to 1/2 times 0 squared plus c. On the left-hand side, -3 squared is 9, and then half of 9, that would just be 9/2 equals. On the right, 0 squared is 0, half of 0 is 0, 0 plus c, so I get my c is equal to 9/2. All right, so I've solved for c. Step 4 is going to be to plug c back into this equation right here. Now I know what c is. So I have 1/2 y squared is equal to 1/2 x squared plus 9/2. And then step 5 is going to be to isolate y, or isolate our dependent variable, in this case y. So the first thing that I'm going to do, just to make my life a little bit easier, is I see that everything is 1/2, 1/2, 1/2. So I'm going to multiply this whole equation by 2, right? So then I'm going to end up with y squared is equal to x squared plus 9. Just a little trick to make my life easier. And then if I want to undo something that is squared, I have to square root both sides of the equal sign. So I'm going to get the square root of y squared equals the square root of x squared plus 9. So then I know y is going to be equal to plus or minus the square root of x squared plus 9. Now this happened in the first half of our notes when we had that absolute value and we had the plus or minus. We only want one of these and we have to figure out which one is correct. So we go back to our initial condition and we ask ourselves right here, which one, meaning the plus or the minus, satisfies the initial condition 0, -3, right? When I plug 0 in for x, which one is going to give me -3 for y? Is it going to be the positive square root or is it going to be the negative square root? Well, let's check. If I plug in 0 for y, right, and I want y to equal -3, I need to choose the plus or the minus. Well, if I want this to equal -3, then I need the negative in front of there because negative square root of 9 would be -3, right? So that tells me that I need the solution that has the negative. So my solution is going to be y equals negative the square root of x squared plus 9. So you always go back at the end if you have a situation where you have a plus or minus like that and you have to choose, you use your initial condition to figure out which one is the correct solution for your circumstances. Okay. Example 5. Ooh, we've got some trig in this one. We have du dt is equal to 2t plus cos t all divided by 2u. And then we have this initial condition here again, which is when t is 0, u is negative 5, right? And then since my variables aren't x and y, I'm going to identify that t is our 0 and u is our negative 5 for our initial condition. All right, step 1, I'm going to separate. So I start with, I have du dt is equal to 2t plus cos t, and that's all upstairs, divided by 2u. So this one's pretty easy to separate, right? We're going to multiply both sides by that 2u to get that out of the denominator. So we're going to have 2u du on the left is equal to 2t plus cos t times dt on the right. Okay, step 1 is done. Step 2 is going to be to integrate both sides. So integrate 2u du and integrate 2t plus cos t dt. On the left-hand side, the integral or the antiderivative of 2u is just u squared. And remember, no plus c on the left, only on the right. So this is equal to, I've got two terms that I have to find the integral of here, or the antiderivative. 2t becomes t squared. And if we've got cosine t, remember the derivative of sine is cosine. So then the antiderivative of cosine is sine. So this would be plus sine t, and then we need our plus c. Okay, step 2 is complete. Now step 3, we are going to use our given initial condition to solve for c. Remember, we've got that ordered pair 0, negative 5, and this is a t value, this is a u value. So when we plug these in, we get negative 5 squared is equal to 0 squared plus sine of 0 plus c. Negative 5 quantity squared is positive 25. 0 squared is 0, and the sine of 0, think about the unit circle, sine of 0 is 0. So I end up with 0 plus c. So that tells me that c is 25. Okay, so then my step 4 is going to be to plug that c value that I just found right back in to my equation from step 2 after I integrated. So I have u squared is equal to t squared plus sine t plus 25. And then the last step is going to be to solve for that dependent variable, which means just getting u alone. And I know how to undo a squared. I just have to square root both sides, right? So I get u is equal to plus or minus the square root of t squared plus sine t plus 25. And now again, I have to make a choice here. Do I want the positive or the negative? So I go back and I ask myself, which one satisfies my initial condition? Right? Which one, the plus or the minus, makes that initial condition true when I plug it into my equation? So I'm going to go ahead and do that. I'm going to plug those in, and I get negative 5 is equal to plus or minus the square root of 0 squared plus sine of 0 plus 25, right? So I get negative 5 is equal to plus or minus, this is 0 squared is 0, sine of 0 is 0, right? So I just end up with the square root of 25, right? So if I need this to equal, whoops, sorry. If I need both sides to be equal to negative 5, then that tells me that I need the negative in front of the square root. So my answer is u is equal to negative the square root of t squared plus sine of t plus 25. And there's my solution for example 5. All right, one more to go. On to example 6. Ooh, this one, the notation is a little bit different. They're giving us y prime notation instead of the Leibniz notation, but doesn't matter. It's the same thing, right? and we're given an initial condition, which is, whoops, 1, 2, meaning when x is 1, y is, whoops, y is 2. All right, so step 1, I am going to separate. So I'm going to switch notations. dy dx is equal to the natural log of x divided by x times y. So I'm going to separate my variables. If I want to get that y out of the denominator, I need to multiply by y. So on the left, I will have y dy equals, and then on the right, I've got natural log of x, still divided by x, I still have that x underneath it, times dx. Okay, now I am going to integrate both sides, right? So step 2 is going to be to integrate. So I've got the integral of y dy equals the integral of ln x over x dx. Okay, on the left, the integral of y, that's just going to be 1/2 y squared. Ooh, but on the right, this may require us to do a little u substitution here because we've got multiple stuff going on. So I am going to let u be natural log x, okay? Then du would be 1 over x dx, which there's our 1 over x in the denominator, and there's our dx, okay? So that means that this side is just going to be the integral of u du, okay, which u is ln x, right? So I end up with 1/2 y squared equals 1/2 u squared plus c, but u is ln x, so I go ahead and plug that back in, and I get 1/2 y squared is equal to 1/2 natural log x squared plus c. All right, so step 2 is done. Now step 3, I need to use my initial condition that I was given to solve for c. So bring down my ordered pair here, which was 1, 2, right? So if I plug that in, I'm going to get 1/2 times 2 squared is equal to 1/2 times the natural log of 1 squared plus c. On the left, 2 squared is 4, half of 4 is 2. So I get 2 equals 1/2 times, natural log of 1 is 0. So 1/2 times 0 squared plus c, well, that's just 0, right? So I end up with c equals 2. Step 4, I go right up here, but I now plug in that c value. So I have 1/2 y squared is equal to 1/2 natural log of x squared plus 2. And now I have to solve for my dependent variable, which is y. So if I multiply everything by 2 to begin with, that's going to be my first step here. Just multiply everything by 2. Then I get y squared is equal to natural log of x squared plus 4. And as I know, I need to square root both sides. So y is going to be equal to plus or minus the square root of natural log of x squared plus 4. And if I use my initial condition to determine which one I want, what you're going to find is that the positive root is the one that satisfies our initial condition. So we end up with y equals the square root of natural log of x squared plus 4.